Hey everybody, doing a introduction of the code base from Ammalgam. This is our first version of our code, and just very high level before we get into the actual nitty gritty of the code, a brief explanation of Ammalgam. We've taken the Uniswap v2 contracts that allow for swapping, and we've built a lending protocol into them. So we allow borrowing of the assets in the market making position. We also allow for people to deposit one asset or the other to earn fees from lending. And lastly, we allow people to borrow the individual tokens and also the market making position together. So that's sort of the feature set, and I'll jump into the code. First thing, just the README, some very helpful instructions. Just know there's some issues if you don't skip. This skip contract is actually something that we use in a test that doesn't compile well, so just skipping this should alleviate that issue. If you don't use let me just get the exact command. The optimizer and optimizer run set to 1, it won't fit. So we had some size constraints. The code that we wrote doesn't really fit well into one contract, and we've had to do a few major refactors to get it to all fit. And we made the trade-off of less optimizer runs just to get the amount of code we wanted into less contracts to have less external calls. The sort of high level, like where everything starts from, is the Ammalgam pair. And this has the main functions to interact with the protocol. Mint, which is similar to Uniswap v2, where you're putting a 50-50 split in value of the two assets, and then getting a receipt token representing that deposit. One thing, all of our deposits and minting involve the pattern of first sending the tokens to the contract and then calling mint. So we do have peripheral contracts that support that. They're not in scope for this audit, but whenever interacting with a pair, you have to send the tokens first and then call mint, similar to Uniswap v2. And then burn to undo mint, get the tokens back, swap. Some helper methods for swap. Deposit, where you're putting in one token or both tokens, but these tokens would not be available for swap fees, just lending fees. Withdrawal, to undo the deposit. Borrow, to borrow one token or the other. Borrow liquidity, which is borrowing the AMM token. So your debt is denominated in L, or the square root of K, from the formula X times Y equals K, rather than X or Y. We have somewhat of an opinionated view here, in the sense that there's not really much purpose of borrowing AMM shares unless you also withdraw the underlying tokens. So this function can kind of be thought of into two steps. One, that are all bundled together in this one function, where you're borrowing AMM tokens, and your debt's denominated in those shares, and then you take those AMM tokens and you withdraw them from the protocol. So it actually will send you the underlying X and Y associated with those shares, And then when you repay, you need to repay both X and Y, but the denomination of those X and Y will be dependent on the price. And then repay and then repay liquidity are sort of the main interactions that you would have with a pair. There's some leftover functions. And then I guess before I get into that, then we have liquidation. There's 3 forks to the liquidation call, depending on what type of liquidation you're performing. A hard liquidation, which can be considered like any liquidation that you're repaying a debt and expecting collateral back. A soft liquidation, which not a huge fan of this name, but has to do with the saturation library, and I'll get into this more later. Basically, the expectation here is that the liquidator is getting paid very minimally, just gas costs, to update the position in our saturation library that manages risk and basically keeps track of where each position would get liquidated and makes sure that in the area it would get liquidated that there's not an oversaturation of that liquidation risk. And so the way we track that, we give an upper bound of like how much risk something's taking up, and as fees accrue over time, that upper bound will eventually get exceeded, and then as it gets exceeded, there's a higher and higher premium that is given to, or higher and higher fees, I should say, not necessarily premium, but that are given out of the position to the liquidator for updating this position in the tree. Alternatively, users could call like sync, or actually I think it's skim, with their address to do this automatically for themselves instead of paying the gas fees to somebody else. But if they choose not to, this happens ever so often as their position grows enough. This also has really important properties if there's too much risk and the fees for that risk start kicking in. Get into this later when we talk about saturation and the risk functions we have, but this will help to automatically resolve that risk if it builds up, if there's too much buildup. And then leverage liquidation is the last type. So liquidate hard, liquidate soft, and the last one is liquidate leverage. So the liquidate leverage is to, in the case where you deposit market making liquidity in the form of X and Y, and then you borrow X and Y against that, there's a point at which we stop allowing you to take more leverage. It's basically, if you think of the principal, or if you take the total deposit minus the total borrow, you have the principal. When the principal is 1/100th of the total deposit, that's the max leverage. And as interest or fees accrue, even the price change in some situations, this can get exceeded, and this function allows for liquidators to unwind the leverage. So it'll basically, there's no requirement from the liquidator to send funds in this case. It just calculates exactly how much leverage there is and then gives a premium based on how much leverage there is, and then whatever's left, the protocol figures out how to unwind the leverage to a point where it's acceptable. All right, so those are the types of liquidations, and then we get into the actual implementation of those 3 functions. And I think the last ones are then skim and sync. So that's the main interactions with the pair contract. The pair contract underneath it has a really important function called the token controller that it inherits, which has a lot of the functions managing the tokens. It actually has the 6 receipt tokens, So depending on whether you're depositing L, X, or Y, or borrowing L, X, or Y, you get a different receipt token. We chose ERC20s instead of doing something 1155 like because, well, at the time we just didn't, I don't really like the 1155 interface, and I thought having 6 tokens was better than having the convenience of having it all in one contract. And we wouldn't have been able to fit the 1155 anyway, so we'd have to figure out something else. But anyway, nonetheless, there's 6 tokens in here. We also have a lot of the balances, so how much is for reserves, and then some timestamp stuff, reference reserves, which has to do with our swap mechanism, our fee mechanism for swaps, which is very unique. I can get into in a bit later. And the total deposits and total borrow assets. These are used to track, shares versus assets. Shares are stored actually on the contract. It's whatever the balance is of the receipt token, and then the assets are here. I actually think we may store shares twice, but anyway, these help us to convert and figure out how much interest is accrued for each. And yeah, so this is just sort of like a helper function where we try to isolate the interactions with the actual tokens to one place. So updating, like burning and minting of new tokens, some helper functions to figure out like what the balance is of for a certain token type. All of this, we do store some of these asset values in transient storage to be able to access them and not have to rerun computationally heavy calculations more than once. And like burn, mint and burn is all handled in this contract. So, but these are called in the Ammalgam pair many places. Getting the reserves, tick range, which is sort of our concept of what the price range is, and some confident interval, and I'm trying to think of anything else that's sort of worth minting or worth discussing at a high level. So so token control and Ammalgam pair are the main 2 files that hold the logic for the actual pair. Now, one of the architectural decisions that we had to make, because we wrote too much code, it didn't fit in one contract, was we split out into a singleton this contract that is, we have calls going from the pair to this contract. And so this contract stores storage for many different pairs. The addresses are the actual pair. And so a pair will call this contract. This contract will look up message sender to determine what data it belongs to. And then it will, return the needed call. So this basically wraps 2 libraries that are rather large, specifically saturation and the geometric TWAP library. So we were able to remove size from the pair contracts by moving these 2 rather large libraries here, and rather than having an external library, we have this wrapper contract that calls those libraries, delegates calls to those libraries. So this will be a singleton. There will just be one version of it that all pairs delegate calls to. And so that's those 3 contracts are sort of the main contracts. There's a factory contract that sort of puts everything together. sort of very similar to the Uniswap v2 contract, except for when it starts to make sure that all of the things are wired together, and it has to deploy, a contract for each receipt token. So a little bit more going on there. So that's the main architecture, I think, at a high level. As far as libraries, we have a constants library that talks about many that has many of the variables that are reused in multiple places. A conversion library, which also has things that we saw getting used in multiple places, so we just put it in one library. So like converting 2 assets from shares, converting 2 shares from assets, some more complicated functions that are used when the borrowed assets start to be meaningful and we can no longer honor the invariant curve, which we call depleted asset protection, and there's documentation of that in our docs on our website that goes more into depth than I want to in this video. It's already at 16 minutes. The geometric TWAP library serves the purpose of tracking the TWAP. So we actually use the V3 version of geometric TWAPs, where you're tracking the not the average, but you're multiplying everything together and then taking a root to get the average rather than summing everything up and dividing. So that's why we call it geometric. This tracks 2 TWAPs. One is a shorter term that we call the midterm interval, and one is the long term. So there's these 2 arrays, one for the midterm cumulative sum and the midterm time interval, and then one for the long-term cumulative sum and the long-term time interval. So what we do with these 2 TWAPs and the current price and the last block price, those 4 price values, we create a min and max price. And whenever we create a new loan, we check that the min and max, we use the least favorable price from the min and max to value the assets against each other. So depending on which way you're converting, maybe X to Y versus Y to X, you would use the min or the max price, or the min and max tick that gets converted to a square root price. That's basically how the high level explanation of what this library is. The interest library is where we accrue interest. There's some Desmos files that also show like the curves that we use, because we use a one-size-fits-all curve, trying to minimize configurations in the protocol as much as possible. And so, the biggest differentiator is that when we accrue interest, borrowed liquidity has a different schedule than borrowed X or Y, and it's only different by a factor of 5. So whatever the utilization is of X, if L had the same utilization, then it would have a 5X interest rate, because we think that asset is just more valuable and should be when you borrow liquidity, it takes liquidity out of swap reserves, and so LPs don't earn swap fees on that borrowed liquidity, and so we think that is important for it to have like a 5x more. So I'm not really sure what else to say. There's 3 different utilization rates, X, Y, and L, and this manages sort of all that, figuring out the utilization rates on those 3 assets. And then, basically figuring out also taking like the protocol fee, and figuring out how much is owed for each of those, taking that amount owed and increasing the assets for the borrowers, and then also increasing the assets for the deposits by that single amount to, you know, transfer value from one pot to the other. Liquidations is probably something that I could probably make a whole video on this, but just for a high level, the way hard liquidations work is we evaluate the positions, any positions, loan to value, and then use a Dutch auction where basically the premium is determined by how far the loan to value has exceeded the 75% loan to value threshold that is allowed. One other caveat here is we actually start the Dutch auction before 75%, but anything before 75% loan to value would actually get a discount instead of a premium. So essentially, if it were to be repaid, the liquidator would get back less than they repaid because the position is still in bounds. The reason for this, and it actually starts at 60% loan to value at a 0%, like you would get nothing. You'd liquidate and get, you know, if it exceeded 60% by a little bit, you get 1% back. The reason we do this is in the case of a price getting manipulated, there are situations where even though the protocol is showing, say, a 65% loan to value, 70% loan to value, somewhere in this range of between 60 and 75, the actual value of those assets would allow for this liquidation to happen at like a market rate. And what that does is, in the case of manipulation, it reduces any value to the liquidator of creating a manipulation, because the liquidation will still occur near market rate. So the person getting liquidating will get basically all their assets back, but we had to create this discounted liquidation in order to ensure that happens. Quadratic swap, this is just like not a lot of code, but very dense as far as the complexity here. What this does is it creates a variable swap fee. So the swap fee is not fixed as in most protocols. The swap fee is based on how far you change the price. So the more you change the price from a reference price, which is determined at the start of the block, the higher your swap fee is. And it's also, I think the right term is transitive, where if like two swaps execute in the same direction, their cumulative fee will be the same as one swap that goes that same distance. So this essentially keeps increasing the price, or the swap fee, the further you move away from the price, to accomplish two things. One, the cost to manipulate the price is no longer trivial. The benefit of changing a TWAP oracle, say on like Uniswap v3, if there's lending using that oracle, the benefit can far exceed the cost of the bips, the swap fee. In this case, that's no longer true, because this maxes out at a 40% fee. And I shouldn't even say max out. That's just sort of when the fee stops growing. So you would pay a 40 fee. I can't remember the exact numbers, but like I think you like double or triple the price. Actually, there's probably something in the notes here that like 9x price change would be a 40% fee. Yeah, so if you 9x the price, not double, you pay a 40% fee. And so this just significantly increases the cost to manipulate, and also in a centralized, decentralized arbitrage of price, where say Binance price changes very rapidly in the centralized on the centralized venue, and then there's an arb to the decentralized exchange. This extracts much more value from that arb, and then also allows prices to be very low when swaps don't have an impact on the price. So it sort of somewhat algorithmically determines the difference between informed and uninformed order flow. Okay. Saturation is also something that I could do like a whole 20-minute video on. We want to actually, the mechanics are still, we're working this out, but we want to offer additional incentives for any issues found in this library, just because we want people to prioritize spending time on it. There's definitely quite a big explanation with some latex in the middle of it explaining this, but if I had to explain this very quickly for this call, it's almost easier to do this in Desmos. I don't know. Oh, I'm recording one window, so I can't do this. But I'll share Desmos links to this. But you can think about this as like tracking, sort of like ticks in Uniswap v3, but large ticks. So we actually we call them tranches, and tranche is 100 ticks. And also, just another side note, we don't use the same tick distance that Uniswap does. We change that as well, but I haven't gotten to that library yet, and I can talk to it when we get there next. So we have these large tranches, and we basically use these tranches to measure what would get liquidated in that area. So when a new debt is created, we calculate where it would get liquidated, where it would start getting liquidated, where it would end getting liquidated with the current reserves available. And then we basically put that liquidation into tranches, similar to putting liquidity into Uniswap, but in this case, it's actually like debts that would get liquidated and where they get liquidated. And then we limit how much can be liquidated in any given tranche by how much reserves there are available in the protocol itself. The max is 90%, but it can go higher to actually 95%. The only way you can get to this 95% is if a liquidity provider withdraws liquidity, or somebody borrows liquidity, would you get to this 95%. And then once you've actually gotten to 85%, we start charging fees per tranche for anyone that is above that 85% threshold. Those fees are variable depending on how close you get to the 95, and they're quite excessive. Basically, the calculations at a high level is if the LP, because if this hits 95%, people can't withdraw liquidity and people can't borrow liquidity. So we need to charge fees sufficient that would be sort of equivalent to what those LPs would earn, say if 90% of the assets would be borrowed, 90% being the max of how much you can borrow of any one asset. So the most you can borrow is like 90% of all the assets. And so we look at that rate, and then we figure out how to charge these tranches that are in this penalty zone enough to compensate the liquidity providers. So this has got a lot of problems in it, computer science wise. We basically have to keep saturation or how much of each tranche is used with respect to the total liquidity in a sorted list, and we actually use a tree structure to do this, so that we can have a sorted list, and when we remove something, we can find the next highest saturation in constant time. because we're using a tree structure, and also we borrowed a function from Mangrove, who also solved this problem in constant time with a different data structure. So I'm going to stop there. Like I said, I could make a whole video on this, and so the brevity of I think this is like 1,600 lines of code is unfortunate for trying to make a 20-minute video that's now 30 minutes long. The TickMath library is very similar to Uniswap's TickMath library, except for we rewrote it for two purposes. One, we got the domain of the tick size down to int 16 instead of int 24 by using a different tick spacing. Our tick spacing is close to about 2 bips, I think. I could be wrong. I'm very bad with precise numbers, but it's all in here. For not knowing the precision, I wrote most of this myself. The only difference, I would say, there's a few differences, is the tick spacing, the int16. Also, a lot of times we have a price and we want a tick, and so we have this function called get tick at price, rather than Uniswap just has the get square root at price, or get ticket square root or whatever. So it's a little bit different because we have a price and then we convert it to a tick, and in Uniswap v3 they never have that. So yeah, that's basically that. Also in the constants, our tick is defined by this basis. So you take a base and raise it to the power of the tick to get a square root price. And this little write-up here shows that our precision is much better because of the not using decimal like Uniswap does. We actually use this sort of format of 2 to the 9 divided by 2 to the 9 minus 1, which has much nicer properties as far as precision with small ticks than the Uniswap v3. Okay, moving on, token symbol. This isn't really important. It's a helper method for just the name of the tokens and being able to put it into the pair name when we create a new receipt tokens. This set utility, I think we borrowed heavily. We link the source of the code that we took from either wholesale or majority of. This is used in the saturation library. And then validation is where we compare, the debt to the collateral to determine whether it meets the loan to value. And this gets reused in a lot of different places. So a few things to note here is, especially in the case of like market making exposure, debts and borrows, we don't sort of, if you mint liquidity and then borrow in the form of market making liquidity, and you borrow one asset against it, we don't just take the mint and the borrow and then compare the two. We first net out the X and Y, and then we figure out which X or Y is a net debt and which is a net collateral, and then we do the conversion. So if you, for example, ETH is trading, I think, near like 2,500 today, and so if you had like 2,500 in one ETH in a market making position, and then you borrowed 2,000 from that, that 2,000 wouldn't result in a net debt. You would still have like leftover 500 USDC and your whole ETH. And so there's no net debt, and so there's no loan to value. For the purpose of liquidations, there still is tracking of that in the saturation library, because eventually if the price moves enough, your borrowed 2,000 could be not enough, as the price changes and maybe you end up with less USDC and more ETH if the price of ETH drops. And so that could eventually form a net debt, but at origination of the position, there's not a net debt. And so we check that, like I said, by netting out the values first and then comparing loan to value. And then also we check the leverage of the position. So those are like the two things going on in here. And then another important thing is we also increase by slippage. So whatever that net debt is during a liquidation, we think about the current liquidity available, how much slippage would occur to sell, to basically buy the debt asset that you would do in a liquidation, because you take the collateral, you'd sell it for the net the debt and then repay the debt. So then we increase the debt for the amount of slippage that would occur during that. We also use this same increase when we calculate liquidations. So it tries to offset the slippage and of the liquidation. Okay, so that's the libraries and the main functions. I think I'm at 36 minutes, so I'm gonna stop that there. And happy to answer any other questions. I'm sure there's many. I'll also try to get as many links to different calculators we use to model these things as I can to share, as well as our docs are available and they're getting refreshed very soon. So I bet by the time you're starting to look at our code, it's already been merged, the refresh, so that should be ready to go. So looking forward to all the issues that you guys can find and responding to them, and very, very excited for your participation, and thank you for taking the time to look at our code.